Okay, so we're back again to look at logarithmic functions and their graphs. So this is just a summary of the transformations. The key points I want to point out are that if the vertical asymptote will always be at x equals 0 for the parent function, but if you move it, horizontal shifts. So if you had your log function here originally, and let's say you moved it this way, do you notice that your domain, this is the domain, right, for your original function, and then, now let's see, different color. If I move it over, do you notice my vertical asymptote also moves over, and so my domain changes, doesn't it? All right, so that's why you need to keep track of the vertical asymptote and look for those horizontal shifts. They're the ones that are going to change your domain. All right? Vertical shifting, I could take this graph here and shift it up, and that's not going to change my domain. All right? So keep that in mind. Let's move on to the next one. All right, so here's another reflections. If you do a reflection on the x, what we saw before, so that's a horizontal reflection, so that's going from here over here, so your domain definitely will change. Instead of going from 0 to infinity, it's going to be negative infinity to 0. The vertical asymptote, if you haven't shifted it horizontally, will stay at x equals 0. Take some time to read over these. There's a lot of information, but you know most of it, and we're now just applying it to a different type of function, the log functions, all right? All right, so here we've got another matching, similar to what we did with the exponentials. And so we need to match the graph to the function. We have a, b, c, d, and e, and we have functions d, f, g, h, and j. So remember in the last video, at the very end where I showed you an example, there was an example there where different bases for the logs. And we determined that a smaller base on a log means it increases faster. So you remember it looks something like this. There was one there was one there, something like that. And this was maybe a base 10, and that was a base 2. So smaller base, faster growth. All right? Smaller base, faster growth. That's the key point here. All right, so I think to approach this, I bet you guys are guessing what you need to look at. You need to look at the base of each of these. So let's look at the base. I'm going to write down base right here. This one, do you remember what that is? You don't write the 10, but it's there, isn't it? The 10. So that's base 10. This one's ln, so that's e, which is approximately 2.817. I think it's 718. 718,817. Anyway, it's more than 2. 718. You have a key on your calculator, little e, and if you ever need to know what it is, just get that little e and hit enter, and it will give you what e's value is. This one has a base of 2 right there. This one has a base of 5 and a base of 25. All right, so if a smaller base has faster growth, this is the fastest one, isn't it? A. So let's pick out the smallest base. Well, I think that's G. So that one goes with A. Then B has to be the next smallest, which would be F, because 2.78. And then 5, so that'd be C. And then 10, so that'd be D. And 25, so that would be E. All right, not too difficult. So you may have a homework problem like that. So keep that in mind. Smaller base, faster growth. All right, let's try another matching one. Now this one has transformations. And so I want to look at, well, those graphs look all over the place, but let's look at the functions f, g, and h, and let's see what's different about them, because anytime you're going to be matching graphs to functions, that's what you need to determine. What is the difference between the functions, between the graphs? Okay, so I'm looking at this. They are all base 4. So there's no difference there. They all are like x plus 2, aren't they? So they all have a horizontal shift. What is that? Left? Left 2? Shift left 2? They all have the same shift, don't they? All right, then we've got some minuses here. That's a reflection, and that's a reflection. This one only has the shift, doesn't it? So I think we could probably pick out h of x first. Remember, our base function would go through 1. Look something like, oop, that doesn't look so good. Let's try that again. Would look something like this, right? That would be our base function. So let's look at A, B, and C, and it looks to me, I'm looking for one that goes left 2. So here's the point I normally would have. Looks like I match right up with that red one there, the A. So I'm going to erase my one I just put on there. All right, do you see that that would match up directly with this A? So this one is A. All right, so F and G. Well, let's look at G. G is just, it's got the minus on the outside, right? So that is a reflection across the x-axis, isn't it? So let me put in my base function. Maybe I should have left it there. There's my base function. Let me make it solid right here. There's my base function. Oh, I don't need that. That's right, because it's shifted 2 also. So I'm looking at A here then. And it's shifted 2 to the left, and then it's reflected 2 to the left, and then reflected. So that looks like C to me. Doesn't it look like C to you guys? Right here, this one? I think so. I think it looks like C. So I wrote all over this. Let me erase it. So this one would be C. And that means the last one's B. All right, well, we still should look at it, even though by process of elimination we know it's B. Okay, so here's A. This is the one that's shifted. And so B is reflected across the y-axis, right? So that means that this point right here, this point goes across the y-axis, so it ends up right there. And so you can see how it matches up with B. Here's B. See how they match up? So that one is B. All right, let's try some more. Now we're going to graph some using our transformations. So remember, this is log base 2, so I know I'm going to have a point at 1, 0, and then I'm going to have another point at B and 1 right here. And our b is 2. So b and 1. And then so this is our basic function here, our base function, or parent function. So that's our parent function. That's log base 2 of x. All right, so that's the one we're going to start with. And then I'm going to look back here and I'm going to see the only difference is that I'm going to be shifting it up 2. So each point goes up 1, 2, 1, 2. All right, and so it would look like that. That would be my f of x. All right, the vertical asymptote is right here. Vertical asymptote at x equals 0, and it doesn't change. So our domain remains the same from 0 to infinity. All right, that looks good. All right, let's look at the next one. Again, base 2, but this time we're adding 2 right in there with the x, so that is when we add 2, we go left 2, we go to the negative 2, and that's because we have x plus 2 has to be greater than 0, so that means x has to be greater than negative 2. So that's our domain, guys, negative 2 to infinity. And that also means that our vertical asymptote is now at x equals negative 2, right here. X equals negative 2. All right, so to draw it in, since it's just shifted over 2, I go back to my original, my parent function, which is this, and I say I need to go that way, 1, 2, right there. Oh, let me change the color. Right there, and this one moves over 1, 2, right there. Now you notice the domain, we've already figured it out, the domain does change because we had a horizontal shift. Horizontal shift. Anything on the horizontal is going to change your domain. All right, let's look at the last one. Let me put in my base function. This one's going to take, I may have to erase a few and change it up a little bit. But there's my log base 2 of x. It looks to me like we have x minus 2, so that's a shift right 2. Then we have a negative here, which means we're going to reflect across the y-axis, x-axis. Negative on the x would be the y-axis, so this is the x-axis. And then we're going to go up 2, and that's the order I'm going to do them in. So first off, my domain comes from the x minus 2 has to be greater than 0. So that means x has to be greater than 2. So my domain is going to be 2 to infinity. So my vertical asymptote is going to be 2 right here. X equals 2. That's where it's changing to. All right, and that right 2 means I take each of these points and I go over 1, 2, 1, 2. So that's the first one. All right, the next one is we're going to reflect it across the x-axis. So this point is on the x-axis, so it stays there. But this point is going to go the opposite side. So it's going to go down here. All right, so it's going to look like that instead. You see the reflection? All right, so that's the second step. So we did, this is step 2. This was step 1. Now we're going to go to step 3, and looks like it's getting a little bit messy. I'm going to get rid of some of it. I'm going to get rid of the purple one. There we go. And let's see, what are we doing? The last thing we're doing, step 3, is we are, change it to green here. We're going up 2, so that's step 3. So that means each of these points we had, we're going to go up 1, 2, right there. 1, 2, right there. And so it's just going to be shifted up a little bit, so it's going to look like that. So that's our f of x right there. Okay, that was a 3-step process. That was a little bit rough, but I think we did okay. All right, so check back for the next video. We're going to do some applications.